Hi, it's Dr. Harris. I'm back with our beginnings of Chapter 5 in our textbook in our MAT111 statistics class. So far in the course, we've talked about some basic data analysis techniques. We've talked about a little bit of probability, and we've looked at a couple of examples of random variables. Now we want to kind of try to tie a lot of that together to begin to see how we're going to uh, learn to say intelligent things about populations. And so chapters 5, 6, and 7 are going to form the heart of our course. And it's an area we're calling inferential statistics. And so here in chapter 5, we're dealing with what we might call the foundations of inference. We're going to introduce our two primary inferential techniques, and we'll look at a few examples. So let's get that ride started. So a couple of terms, I've introduced these in class already, but I want to remind you of them. The term parameter is one that we use it stands for a number. It means a number that describes some aspect of a population. So parameter talks about a population, whereas a statistic is going to be a number that describes an aspect of a sample, a subset, data that we've collected from a subset of the population. You'll see the term point estimate in our textbook, and we want to recognize that for many purposes, point estimate is a synonym for statistic. And basically, as I've written here, it suggests that a statistic is being used to estimate the value of a parameter. So let's talk about the two primary types of parameters that we're going to be interested in this class. They're going to be the population mean and the population proportion. So we're familiar with means. We know that we are adding a bunch of numbers together and dividing by the number of numbers that we have. And so it stands to reason then that a mean is going to come about from numerical data. And the other type of parameter that we're going to be primarily interested in this course is a proportion. And what we mean by proportion, we're talking about the fraction of a population that possesses some sort of characteristic, or as I say here, meets a specific condition. So what we're doing is we're really asking, is the condition met? That's in some sense a yes or no question. And so we're going to see the proportions are going to come up when we have categorical data. We're going to use the Greek letter mu to stand for a population mean. And we're going to use the letter that we're used to, P, for a population proportion. So we've got Greek and ordinary letters that we'll be using from time to time in various ways in our work here. So this is something else I believe I've mentioned already. The reason why we look at statistics rather than try to figure out what the exact value of a parameter is that it's too costly to actually gather information from all individuals in the population. It's too time costly, too money costly, maybe both, but it's too much work to get the information from the entire population. So what we do, we draw a random sample, we compute a statistic from that sample. So X bar is the symbol that we use for sample means, and we're going to use P hat. So P with a little caret over it, pronounce that P hat to represent a sample proportion. So mu is the population mean, X bar is the sample mean, P is our population proportion, P hat is our sample proportion. We'll be using these symbols a lot. Hopefully you'll get pretty used to them. So here are a couple of questions, studies that we might be interested in conducting. And in each case, I'm asking, are we interested in a mean or a proportion? In the first one, we're collecting information about the presence of white nose syndrome, which I've noted here as a disease that can occur in bats. So we've gathered 100 bats and we've looked to see whether or not they have white nose syndrome. And so the question is, in this instance, are we interested in a mean or proportion? Our second study would be to maybe look at either those same bats or a different sample of 100 bats, and we gather information about what their wingspan is. And so the question is, are we interested in a mean or a proportion in this instance? I'll give you just a few seconds to think about this. You can stop the video as well and try to answer both these questions. So I'll give you just a brief period of time before we answer them. In the first question, we're asking, do they have the disease or not? So hopefully we can recognize that yes means they have the disease, no means they don't. And so we're collecting categorical data from the bats in this instance. Do they or do they not have the disease? And so in this case, we're interested in the proportion of bats that have white nose syndrome. In the second question, what we're gathering is we're gathering the value of their wingspan. That's a number. So we're gathering numerical information, how long it is from one wingtip to the other for these bats. And so since we're collecting numerical data, that means that we're talking about a mean, in this case, a population mean, the mean wingspan for those bats. So just briefly, I'm just going to show this table here. We're going to come back to this much more in chapters 6 and 7. But there are 5 different parameters that we're going to be interested in this course, 2 of which involve proportions, 3 of which involve means. And so we'll be seeing a little bit about one proportion throughout the rest of chapter 5. In chapter 6, we'll do more examinations with both types of proportion examples, one proportion and the difference of 2 proportions. And in chapter 7, we'll deal with all 3 of these mean scenarios. So in the rest of this chapter, we're going to be working with proportions only. And so here is the scenario that we want to imagine at the moment. We have a population that we're interested in, and we're interested in determining the proportion that the population has of some particular attribute. If we don't survey the entire population, we won't know the exact value of the population proportion. And so we're expecting that value is unknown to us. But we want to be able to try to say something intelligent about the value of that proportion. So here are the 2 types of questions that we're going to be looking at in slideshows 3, or in videos 3 and 4 for this chapter. The first one, which will come up in the third video, is how can we come up with a range of values that we think it's reasonable to conclude that the population proportion is between. So we come up with a range of values, a low number and a high number, and we say that we're pretty confident, we're pretty sure that the proportion lives between those 2 numbers. That range is going to be called a confidence interval. So confidence intervals are going to be a big thing that we're going to be working with in the third video for this chapter. And another type of question is, suppose that we have in mind a specific question, a specific value for the parameter, and we want to check, is it reasonable to believe that that number could really be the proportion value for the entire population? When we're making a decision about the reasonableness of one specific value for a parameter, we're performing what's called a hypothesis test. And we'll be talking about the logic of that in the fourth video from this chapter. So confidence intervals, hypothesis tests, we're going to be doing these 2 types of statistical procedures over and over again in these next 3 chapters. But before that, we need to introduce the notion of what we call a sampling distribution. And that's what our second video is going to focus on, is trying to get a little bit of a handle on what we mean by sampling distribution. So if you take a sample from a population, you're going to get a particular value of a sample proportion. But if you took a different sample, you might expect, or you probably should expect, that you're not going to get the exact same value for the sample proportion that you did from the first sample. So we want to get because the sample that we choose depends on random chance, we expect to get a different value most of the time for the sample proportion from sample to sample. And so what a sampling distribution describes is what would the distribution of a whole bunch of sample proportions look like, or sample statistics, but in this case, sample proportions. So if we took many, 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 many samples of the same size from a population, what would the density plot of all the sample proportions that we computed from all those samples look like? So in the second paragraph on the slide, notice that we've got an important point. A sample proportion is an example of a random variable. It's the outcome of a random process. A numerical value is associated with a random process. Same thing would be true if we took a random sample and we had some numerical attribute that we collected from every individual in the sample, and we computed the sample mean. That's an example of a random variable. It's the outcome, a numerical outcome to a random process. So we're computing, in this chapter, we're computing sample proportion after sample proportion. We can imagine computing many different, taking many different samples, computing many different sample proportions, and we're interested in what can we say about the density plot of all those sample proportions. And so that's what we're going to be doing in our next video. I'm going to be moving over to a different slideshow to look at where we might simulate the notion of how we can find a sampling distribution. And so just to set that up, we've got a population, I've got a large population that for which 70% of the population has a particular attribute. Now, I'm not going to be interested in having you work through the code, the RStudio code that we're going to be doing to generate the plots that we're getting, but we will be looking at I will be showing you some code, and in some of that code, we'll be seeing how to draw a sample of a particular size from a population. We can compute the sample proportion from that sample, and then we can actually very quickly generate 10,000, say, different samples from the population. And once we compute the sample proportion for each of those 10,000 samples, we can draw a histogram, a density plot, a bar chart for those 10,000 sample proportions. And that will give us an idea of what the sampling distribution of the statistic p hat is going to look like. And toward the end of that slideshow, we're going to vary the sample size. First, we're looking at sample size 100, but we're going to make the sample sizes larger, and we'll see what we can learn about the sampling distribution, various properties of the sampling distribution based on looking at sampling distributions for a variety of different sample sizes. So with that, I'm done with this video for now. We will go and look at our simulation activity.